3I Atlas is one of the most mysterious visitors our solar system has received in recent times. It is officially the third known interstellar object to pass through our cosmic neighborhood, after the famous Oumuamua and Borisov. It was discovered by astronomers using the Atlas survey, which scans the sky for moving objects and potential hazards. When it was first detected, its speed and trajectory showed that it did not come from inside our solar system. Instead, it arrived from far beyond, traveling through interstellar space for perhaps millions of years before entering the reach of the Sun's gravity. At first, scientists thought it might be just another interstellar comet like Borisov, with a hyperbolic orbit that would take it around the Sun and then back out into deep space forever. But as more observations came in, the behavior of 3I Atlas surprised many. Its path seemed to settle into a pattern that did not look like a simple flyby. The object appeared to be slowing slightly and interacting in complex ways with the gravitational fields of the Sun and the planets. Some models suggested it could remain inside the solar system for much longer than expected. This raised a new and fascinating question. Could 3I Atlas actually stay in the solar system permanently, or at least for a very long time? If so, that would make it the first known interstellar object to be captured into a solar orbit instead of passing through and leaving. Normally, objects from interstellar space travel so fast that the Sun's gravity cannot trap them. Their orbits are open, meaning they enter and then exit again. But in rare cases, if the object passes close to a planet at just the right angle, its speed can change enough to allow the Sun to hold onto it. This is called gravitational capture. It has happened before with comets and asteroids that originated in the distant reaches of our own solar system. Astronomers are studying the trajectory of 3I Atlas very carefully to see if this is happening now. They use telescopes on Earth and in space to track its position against the background stars night after night. They feed this data into computer models that calculate its orbit with high precision. These models take into account the pull of the Sun, the planets, and even tiny effects like the pressure of sunlight and the jets of gas that can erupt from a comet's surface. If 3I Atlas continues to match the path of a bound orbit, it could mean that for the first time we are witnessing an interstellar visitor being captured by our solar system. Avi Loeb, a well-known astrophysicist from Harvard University, has taken special interest in 3I Atlas. He has previously suggested that some interstellar objects could be artificial, possibly created by advanced civilizations. His views on Oumuamua were controversial, but they attracted global attention. Regarding 3I Atlas, Loeb has pointed out that if it is indeed staying within our solar system, this gives scientists a unique opportunity. Instead of watching a fast-moving object race past us and vanish forever, we may be able to study it for years, gathering detailed information about its composition, structure, and motion. There are several possible explanations for why 3I Atlas seems to be staying. One is that it might have passed close to Jupiter or another large planet in just the right way to lose speed. Jupiter's immense gravity has acted like a cosmic net many times in the past, capturing comets and changing their paths. Another explanation is that the original speed of 3I Atlas was not as high as expected, making capture easier. It is also possible that some combination of gas jets and solar radiation pressure helped slow it down slightly. The physical nature of 3I Atlas is still not fully understood. Early observations show that it has a greenish glow, likely from gases like diatomic carbon and cyanogen, which are common in comets and shine green under sunlight. The shape seems irregular, and it is surrounded by a glowing coma, a cloud of gas and dust released as it is warmed by the Sun. There are hints that its core might be larger and denser than Borisov, which was a typical interstellar comet. Some astronomers think it could be a fragment of a larger object that broke apart long ago in another star system. If 3I Atlas truly remains in a stable orbit around the Sun, this discovery will change how we think about interstellar visitors. Until now, scientists believe that such objects only pass through briefly. A captured interstellar body would give us a permanent laboratory in our own cosmic backyard. We could send spacecraft to explore it. We could study its materials in detail to learn about the chemical makeup of other planetary systems. It would be like having a messenger from another star living among us. Of course, this is still an open question. The orbit of 3I Atlas must be observed for many months, even years, before scientists can confirm capture. Small uncertainties in measurements can lead to big differences in long-term predictions. Some experts think the object might still escape eventually, on a long, shallow hyperbolic path. Others believe it has already crossed the threshold into a bound orbit. The key will be precise tracking and comparison with theoretical models. Whatever the outcome, the arrival of 3I Atlas has sparked intense scientific curiosity. It follows Oumuamua and Borisov, showing that interstellar objects may be more common than once thought. Every such discovery gives astronomers new clues about how planetary systems form and evolve. If objects like these regularly pass through and sometimes even stay, then our solar system may be constantly interacting with material from distant stars. The story of the discovery of 3I Atlas begins quietly, like many important astronomical discoveries. Astronomers were not looking for anything extraordinary that night. The Atlas Survey, which stands for Asteroid Terrestrial Impact Last Alert System, is an automated sky-scanning program based in Hawaii. Its main purpose is to search for asteroids that might pose a threat to Earth. It uses wide-field telescopes that photograph large sections of the sky over and over again, comparing images to look for moving points of light. On one of these observing runs, astronomers noticed a faint object moving steadily against the background of stars. At first, nothing seemed unusual. Many small icy bodies and asteroids pass through the inner solar system, and most are quickly classified and catalogued. But when the team calculated its orbit using the first few nights of observations, they found something surprising. The path of the object did not fit the usual pattern of a comet from the outer solar system. Instead, it appeared to be on a hyperbolic trajectory, moving faster than the escape velocity of the solar system. This meant it had likely come from beyond the Sun's gravitational influence. When follow-up observations confirmed this, the object received the designation 3I Atlas. The 3 in its name indicates that it is the third confirmed interstellar object after Oumuamua, which was discovered in 2017, and Borisov, found in 2019. The letter I stands for interstellar. Atlas refers to the survey system that found it. For astronomers, this was an exciting moment. Interstellar objects are rare, and each new one provides a unique opportunity to study materials from distant star systems. Teams around the world quickly turned their telescopes toward 3I Atlas to gather as much data as possible. Observatories in North America, Europe, and Asia contributed. Space telescopes were also alerted to observe it while it was still bright enough. Early images showed a fuzzy coma surrounding the central body, indicating that it was active like a comet. Spectroscopic measurements revealed emissions of gases that are typical of icy bodies warming as they approach the Sun. The first estimates of its speed were impressive. It was moving fast, much faster than typical comets from the outer solar system. This speed confirmed its interstellar origin. Objects formed around other stars can be ejected into space through gravitational interactions, and over long periods they travel between star systems. By the time they arrive here, their paths are not bound to the Sun. They simply swing by and continue on their way. But in the case of 3I Atlas, something interesting happened as more data came in. Astronomers noticed that its trajectory was slightly different from what a simple hyperbolic flyby would predict. There were small but significant deviations that hinted at either complex gravitational interactions or unexpected non-gravitational forces. Some researchers began to explore whether the object might have encountered a planet or some other influence that changed its orbit. Jupiter is often the key player in such situations. Its massive gravity can capture or redirect passing bodies, and many comets have been permanently trapped in the inner solar system after close encounters with Jupiter. Astronomers ran simulations to see whether 3I Atlas could have passed near Jupiter on its way in. Some models showed that a carefully timed encounter could indeed slow the object enough to place it into a loosely bound orbit around the Sun. This idea was exciting because it had never been observed with an interstellar object before. Oumuamua and Borisov both entered and left without being captured. If 3I Atlas had indeed been slowed down enough, it might remain within the solar system for decades, centuries, or even longer, depending on the exact orbital parameters. The discovery of 3I Atlas also led to quick coordination between international observatories. Because interstellar objects travel on unusual paths, it is important to track them as accurately as possible. Observatories shared precise positional data to refine the orbit calculations. As a result, astronomers were able to create increasingly accurate models of its future path. These models are constantly updated as new measurements arrive. At the same time, scientists studied its physical characteristics. They looked at its brightness over time to estimate its size. They analyzed its spectrum to identify the gases in its coma. They compared its activity to that of Borisov, which had behaved like a typical comet from another star system. Some found that 3I Atlas seemed slightly larger and brighter, with a more pronounced green glow caused by specific molecules becoming excited by sunlight. This green color made it visually striking in telescope images and helped to distinguish it from many ordinary comets. The early weeks after the discovery were filled with excitement and debates. Some astronomers were cautious, noting that orbital measurements can change as more data is collected. Others were intrigued by the possibility of capture. If the object truly were to remain, it would give us a chance to study an interstellar visitor not just for a few weeks but potentially for a long period. During this period, Avi Loeb began to comment on the discovery as well. He has long argued that we should study interstellar objects carefully because they might hold clues to advanced extraterrestrial technology or unusual astrophysical phenomena. He noted that if 3I Atlas stays in the solar system, it would be a perfect target for future space missions. A spacecraft could approach it, orbit it, or even collect samples. This would provide direct evidence about the composition of material formed around other stars, something we have never had before. The next stage in the story of 3I Atlas focuses on understanding its orbit in detail. Determining the exact path of an object moving through space is one of the most important tasks in astronomy. For ordinary comets and asteroids that belong to our solar system, this is usually straightforward. Their orbits follow predictable patterns around the Sun, and astronomers have centuries of experience mapping them. Interstellar objects are different because they arrive from outside with high speeds and unfamiliar trajectories. When 3I Atlas was first detected, the initial orbit calculation showed a classic hyperbolic shape. A hyperbolic orbit means the object is not bound by the Sun's gravity. It enters from interstellar space, swings past the Sun once, and then departs, never to return. Oumuamua and Borisov followed this kind of path. But small differences in measurements can change the picture significantly. That is why astronomers quickly gathered as much positional data as possible, using telescopes spread across different continents to watch its motion relative to background stars. Each night of observation added new data points. These points were combined to refine the orbital model. Specialized computer programs simulate the gravitational forces of the Sun and all the major planets to predict where the object should appear in the sky at future times. If the real observations match the predictions, the orbit model is considered reliable. If they differ, astronomers adjust the model and look for reasons for the deviation. For 3I Atlas, these refinements began to reveal something unexpected. The eccentricity of its orbit, which measures how open the path is, started out clearly greater than 1. That means an open hyperbola. But as more accurate data came in, the the eccentricity value moved closer to 1. An orbit with eccentricity equal to 1 is a parabolic trajectory, the boundary between open and closed. An orbit with eccentricity less than 1 is elliptical, which means the object is captured and will keep returning around the Sun. This subtle shift was enough to catch the attention of dynamicists, scientists who specialize in orbital mechanics. They asked whether something had happened to reduce the speed of 3I Atlas after it entered the solar system. One possibility was a close approach to a massive planet, most likely Jupiter. Even a distant encounter can alter a trajectory. If the object passed behind Jupiter relative to its motion, the planet's gravity could have slowed it down. This kind of interaction has been observed with comets that originated in the distant Oort cloud, some of which were pulled into stable orbits after passing near Jupiter. Another possibility involved non-gravitational forces. Comets often eject gas jets from their surfaces as they warm up. These jets can act like tiny thrusters, pushing the comet slightly off its gravitational path. For most comets, this effect is small but measurable. If 3I Atlas had strong localized outgassing, it could have experienced a gentle braking force that helped reduce its velocity relative to the Sun. Astronomers also considered measurement uncertainties. Early observations always have small errors, and with interstellar objects moving quickly across the sky, these errors can make a difference. As the weeks passed and the data set grew, the models became more stable and the uncertainty shrank. The result continued to suggest that the orbit might be shifting toward a bound or nearly bound state. To explore this idea, scientists ran large numbers of orbital simulations, changing the starting conditions slightly to see what range of futures were possible. Some of these simulations showed the object looping around the Sun and staying for a long time. Others showed it eventually drifting out again, but on a slower trajectory than originally expected. The range of outcomes depended on tiny differences in position and speed, which is why continued observation was essential. If 3I Atlas does remain, its orbit would likely be elongated and tilted relative to the plane of the planets. It might resemble the orbits of some captured comets that swing far out and then return after many decades or centuries. Such an orbit would make it a long-term resident of the solar system rather than a brief visitor. This would be a first for an interstellar object. Astronomers are cautious because orbital evolution can be complicated. The gravitational influences of the planets, particularly Jupiter and Saturn, can slowly change the orbit over time. A path that looks bound today might still allow the object to escape after a few encounters. On the other hand, small forces could stabilize it. That is why continuous tracking over years is the only way to be sure. The debate about the orbit of 3I Atlas is not just academic. If the object is captured, it becomes an accessible target for future space missions. Engineers could design a probe that reaches it without the extreme velocities required to chase a fast-departing interstellar visitor. This would open the door to direct exploration, something that has never been done with material from another star system. The orbital studies also have scientific importance. They tell us about the gravitational environment of the solar system and how it interacts with passing objects. If interstellar objects can sometimes be captured, it means our solar system may collect such bodies over long timescales. Some may already be hiding in distant orbits, waiting to be discovered. As astronomers continue to refine their models, they are watching for small signs that will reveal whether 3I Atlas is truly slowing enough to stay. Each update to its position adds to the picture. Space agencies and research groups are planning how best to take advantage of this opportunity. For many scientists, this is a once-in-a-lifetime chance to watch an interstellar object in real time as its fate inside our solar system is decided. The next part of the story focuses on the physical nature of 3I Atlas itself. Understanding what this object is made of and how it behaves gives scientists valuable clues about where it came from and what kind of environment it formed in. When an object from another star system enters our solar system, it carries information locked inside its ice, dust, and minerals. By studying these properties, astronomers can learn not only about the object itself but also about distant planetary systems that we cannot visit directly. From the first detailed images, astronomers noticed that 3I Atlas has a distinct greenish glow. This is a common feature of some comets, caused by specific molecules being broken apart by sunlight and then glowing in characteristic colors. In this case, the most likely cause is the presence of diatomic carbon, a simple molecule made of 2 carbon atoms, and cyanogen, which is a compound of carbon and nitrogen. When these molecules are exposed to ultraviolet light from the sun, they emit a bright green light that can be seen through telescopes. This glow made 3I Atlas stand out in the night sky and helped observers track it more easily. The central body of 3I Atlas is not perfectly known, but astronomers can estimate its size by measuring how bright it appears and how much light is reflected from its surface. These estimates are not exact because the brightness of a comet also depends on how active it is and how much dust and gas it releases. Early calculations suggest that 3I Atlas is larger than Borisov, possibly several kilometers across. Its nucleus may be irregularly shaped, like most comets, with rough surfaces and deep pits where volatile ices evaporate when heated. Spectroscopic studies, which analyze the light reflected and emitted by the object, have provided more information. Observations show a mixture of gases typical of icy bodies, including water vapor, carbon-based molecules, and possibly traces of more complex organic compounds. This fits the picture of a cometary object that formed in the cold outer regions of another star system, where ices could accumulate around a solid core. Over time, interactions with giant planets in that distant system may have ejected it into interstellar space, sending it on a long journey that eventually brought it here. One intriguing feature of 3I Atlas is the strength of its activity. Some interstellar objects, like Oumuamua, showed little or no visible coma, leading to debates about whether they were comets or something else. Borisov, on the other hand, behaved like a normal comet, releasing large amounts of gas and dust. 3I Atlas seems closer to Borisov in this respect, but some astronomers have noted unusual patterns in its outgassing. There appear to be bursts of activity that do not always match simple models of solar heating. This could indicate that its surface has irregular pockets of volatile material that erupt unpredictably as sunlight reaches them. The composition of 3I Atlas may also offer hints about its origin. The relative amounts of different gases can vary depending on the conditions in the region where it formed. For example, if it formed closer to its parent star, it might have less carbon monoxide and methane, which are very volatile. If it formed far out, like objects in our own Kuiper belt, it could retain more of these substances. Comparing its chemical signature with known solar system comets helps astronomers build a picture of what kind of star system it came from. Another interesting aspect is the structure of the coma and tail. As 3I Atlas approached the Sun, solar radiation and the solar wind pushed dust and gas away from the nucleus, forming a tail that stretched millions of kilometers into space. Images from professional and amateur astronomers showed a bright green coma and a faint tail pointing away from the Sun. The shape and direction of the tail matched expectations for a comet moving through the inner solar system, but its intensity varied in unexpected ways. These changes are being studied to learn more about the rotation of the nucleus and the distribution of ices on its surface. The physical characteristics also influence how the object moves. Outgassing jets act like small thrusters, changing its trajectory slightly. This is one reason why tracking comets precisely can be challenging. If the jets are uneven or change over time, the object's path can drift from the purely gravitational prediction. For 3I Atlas, this effect may even be contributing to its potential slowdown, although the exact amount is still under study. For scientists, 3I Atlas represents a natural sample of another planetary system delivered to us for free. Normally, to study material from another star, we would need to send spacecraft on journeys lasting tens of thousands of years. Here, an object from far away has come to us, carrying information about the chemistry and physical processes that occurred light years from Earth. If it remains in the solar system, future space missions could visit it directly, bringing back detailed measurements or even physical samples. The study of its physical nature is still ongoing. As it moves through different parts of its orbit, it experiences changing solar conditions that reveal new layers of material. Telescopes will continue to monitor its brightness, gas emissions, and tail structure. Each piece of data adds to the puzzle and helps build a more complete picture of this remarkable interstellar traveler. The next part of the story focuses on why 3I Atlas has captured so much scientific attention and what makes this object so special compared to the two interstellar objects discovered before it. Every interstellar visitor gives astronomers a rare chance to look at something that was not formed inside our solar system. These objects are like time capsules traveling between the stars. They were created around distant suns, shaped by completely different environments, and then spent millions of years drifting through the dark spaces between star systems before arriving here. When Oumuamua passed through in 2017, it surprised everyone because of its unusual shape and behavior. It showed no clear cometary tail, yet it moved in a way that suggested some kind of non-gravitational force was acting on it. Its elongated form and mysterious acceleration led to many debates about what it might be. But Oumuamua was already leaving by the time astronomers noticed it, so there was little time to collect detailed data. Borisov in 2019 was easier to study because it behaved like a typical comet, but it too passed quickly through the inner solar system and was soon gone. 3I Atlas is different for two main reasons. First, it was discovered early enough that scientists have more time to observe it. Second, and most important, its trajectory may allow it to stay in the solar system for an extended period. This changes everything. Instead of a brief rush to gather data, astronomers can plan long-term observations. They can study how its activity changes over time, how its orbit evolves, and what happens as it interacts with the solar environment. This possibility has attracted not only astronomers but also engineers and mission planners. If 3I Atlas remains in a stable or long-term orbit, it could become a realistic target for a spacecraft mission. Reaching a fast-moving interstellar object that is leaving the solar system is extremely difficult because of the enormous speed required. But if the object is captured or slowed down enough, a probe could reach it using current or near-future technology. This has led to discussions about whether an existing spacecraft could be redirected toward it or whether a new mission could be developed. The scientific rewards of such a mission would be enormous. For the first time, humans could examine material from another star system up close. We could analyze the surface, measure its composition directly, and study its structure in detail. This would help answer fundamental questions about how planetary systems form and how common different types of materials are in the galaxy. It would also help us compare our solar system with others in a direct and tangible way. The interest in 3I Atlas has also extended to theoretical work. Astronomers and astrophysicists are using this object as a test case to improve their models of how interstellar objects travel and interact with star systems. Until recently, most models assumed that interstellar visitors simply pass through. Now scientists are examining how often capture might occur, under what conditions, and what kinds of orbits result. This is important because it may change our understanding of the population of objects in the solar system. There might already be interstellar bodies captured in distant orbits that have gone unnoticed because they are faint and far away. Another reason for the strong interest is the role of 3I Atlas in broader scientific debates. Avi Loeb has suggested that some interstellar objects might be of artificial origin. While most scientists believe 3I Atlas is a natural comet, Loeb has argued that keeping an open mind is important. If the object remains nearby, it can be studied much more thoroughly than Oumuamua, which left too quickly for decisive evidence. A long observational campaign could check for any signs of unusual behavior or composition that would be hard to explain through natural processes. Even if nothing artificial is found, the data would still be valuable for understanding natural interstellar bodies. The excitement is not limited to professionals. Amateur astronomers have been tracking 3I Atlas as well. Because of its distinctive green glow and its position in the night sky, it has become a popular target for backyard telescopes and astrophotography. This widespread observation helps gather more data points that can be used to refine orbital calculations. It also spreads awareness and inspires interest in astronomy among the public. 3I Atlas has become a symbol of how the universe is not isolated. Our solar system is not a closed box. Objects from other stars can and do pass through, sometimes staying long enough for us to study them closely. This reminds scientists and the public that we are part of a larger galactic neighborhood where material is exchanged between star systems over immense spans of time. The coming years will be critical in determining just how long 3I Atlas remains in our solar system. Continuous tracking will show whether its orbit stabilizes or whether it eventually escapes. In either case, the amount of data collected will be far greater than what was possible with the previous interstellar visitors. This makes 3I Atlas a milestone in the study of interstellar objects, and a valuable opportunity that astronomers are determined not to waste. The story of 3I Atlas is also tied closely to how our solar system itself behaves like a kind of gravitational gate, pulling some visitors in while letting others pass through untouched. To understand why 3I Atlas might stay longer than expected, scientists look closely at the way the Sun's gravity and the giant planets shape the paths of incoming objects. When something enters the solar system from interstellar space, it usually moves at a very high speed and follows a hyperbolic trajectory. This means its path is open and it will only make one visit before heading back into deep space. However, if the incoming object's speed and direction are just right, and if it passes near one of the massive planets like Jupiter, its path can be altered significantly. This is called gravitational capture. The planet's gravity can act like a slingshot, either speeding the object up or slowing it down, depending on the angle of approach. In rare cases, this can reduce the object's velocity enough for it to fall into a bound orbit around the Sun instead of escaping. These captures are not easy to achieve because the object has to approach with the perfect combination of speed and trajectory, but they are not impossible. Computer simulations have shown that the solar system might have already captured several interstellar objects in distant orbits. These bodies would be faint, small, and located far from the Sun, making them extremely difficult to detect with current telescopes. But with improving technology and more dedicated searches, astronomers are starting to find hints that some of these distant bodies may not have originated here. 3I Atlas could be one of these rare cases where the trajectory and interactions align just right to make it linger within the Sun's gravitational influence. One of the key players in this process is Jupiter. Because it is so massive, Jupiter acts like a cosmic gatekeeper. Many comets from the outer solar system are redirected by Jupiter's gravity, either inward toward the Sun or outward into deep space. For interstellar objects, Jupiter's influence can determine whether they stay longer or not. If 3I Atlas passes close enough to Jupiter at the right time, its velocity could be altered in such a way that it transitions from a hyperbolic path to an elliptical, or even highly elongated bound orbit. If this happens, the object would no longer be just a visitor but would become part of the solar system for an extended period, possibly thousands or even millions of years. Astronomers have been running orbital models for 3I Atlas to explore different scenarios. These models use precise measurements of its current speed, position, and direction to project its future trajectory. Early results suggest that it has a lower excess velocity compared to many other interstellar objects, which means it is moving more slowly relative to the Sun. This increases the chance of capture. The exact outcome depends on future gravitational encounters, especially with Jupiter and possibly Saturn. Another factor is how outgassing might affect its orbit. If 3I Atlas behaves like a comet and releases gas and dust as it gets closer to the Sun, this can create tiny but continuous forces that alter its trajectory. These non-gravitational forces can either help keep it in a bound orbit or push it away, depending on the direction and strength of the jets. Tracking these effects over time will help refine predictions. The possibility of capture is exciting because it would mean that for the first time, astronomers could study an interstellar object over many years. Usually, these objects give only a brief observational window. With 3I Atlas, if it stays, telescopes could watch how it changes as it travels through different parts of the solar system. It might become less active over time as its volatile materials are depleted, or it might surprise observers with unexpected behavior. There is also a historical angle to this idea. Some scientists have proposed that interstellar objects captured in the distant past may have played a role in shaping the solar system. They might have delivered unusual materials, or even helped seed planets with compounds that contributed to the development of life. If 3I Atlas is captured, it would give scientists a living example to study these processes in action rather than just theorizing about them. The study of 3I Atlas is also improving our broader understanding of how common interstellar visitors are. A few decades ago, many astronomers assumed these events were extremely rare. But the discoveries of Oumuamua, Borisov, and now 3I Atlas within a relatively short time suggest that the galaxy may be filled with countless wandering objects, and that our solar system is constantly being crossed by some of them. Most are too small or faint to notice, but modern surveys are making detection more likely. As technology advances, especially with the upcoming Vera Rubin Observatory, the detection rate of such objects is expected to rise dramatically. This will give scientists many more examples to study, but 3I Atlas holds a special place because of its unusual orbital characteristics. If it truly remains in a bound orbit, it may become a long-term resident and a scientific treasure for generations to come. The prospect of a captured interstellar object staying in our solar system adds a sense of wonder. It is like discovering that a traveler from another star decided to linger and share its secrets, instead of just passing through silently. For astronomers, this is a rare opportunity to observe and learn in ways that were not possible before. For everyone else, it is a reminder that space is full of surprises and that our solar system is connected to the wider galaxy in ways that we are only beginning to understand. The attention around 3I Atlas has also brought new energy to discussions about future space missions designed to explore interstellar objects. Until recently, most space exploration plans focused on planets, moons, and asteroids that are native to our solar system. But interstellar visitors represent something entirely different. They carry information from distant star systems, and studying them directly would open a new chapter in planetary science. If 3I Atlas remains in a stable orbit, it could be the first realistic target for such a mission. When Oumuamua was discovered, space agencies quickly realized that sending a probe after it would be extremely difficult. The object was already speeding away from the Sun at high velocity, and any mission would have required technology far beyond what is currently available. Some proposed ideas involved using powerful solar sails or gravity assists from planets, but none could be launched in time to catch up. The same was true for Borisov, which moved too quickly and followed a steep hyperbolic path. 3I Atlas, however, offers a very different scenario. If it is captured into a long-term orbit, engineers would not need to chase it at extreme speeds. Instead, they could plan a mission that intercepts it at a predictable point along its path, much like missions to comets and asteroids. This drastically lowers the technological barriers and makes such a mission feasible with current or near-future propulsion systems. Even spacecraft already in space might be able to be redirected toward it if the timing and orbit align. One concept being discussed is a fast response mission that could be launched relatively quickly once the object's orbit is confirmed to be stable. This mission would focus on detailed imaging, surface analysis, and sample collection. Another idea involves using a small fleet of probes to approach the object from different angles, giving scientists a complete view of its shape and activity. Since 3I Atlas emits a green glow and may behave like a comet, studying its gas and dust would be a priority. The composition of these materials could reveal what kinds of environments the object formed in before it left its home star system. Sampling material from an interstellar object would be groundbreaking. The only interstellar samples humanity currently has are tiny particles trapped in the solar system or collected by specialized instruments on spacecraft like Stardust. These provide limited information. A dedicated mission to 3I Atlas could bring back larger samples, or at least analyze them in situ using modern instruments. Scientists could compare the isotopic ratios, mineral compositions, and organic molecules found on 3I Atlas with those in comets and asteroids native to our solar system. Any differences would give important clues about how other planetary systems form and evolve. Avi Loeb and other researchers have also proposed that interstellar objects might occasionally be artificial, perhaps debris from alien technology, or even functional probes. While most scientists believe 3I Atlas is natural, a space mission could check for unusual features. High-resolution scans could look for regular shapes, metallic structures, or other anomalies. Even if nothing artificial is found, ruling out such possibilities scientifically is valuable. It strengthens our understanding of what natural interstellar bodies look like and sets a baseline for future discoveries. Planning a mission to 3I Atlas also inspires new technological developments. Engineers must design spacecraft capable of long-duration operations, flexible trajectories, and precise navigation. Missions to distant comets like Rosetta have already shown that such challenges can be overcome, but a mission to an interstellar object would push these skills further. It might involve autonomous navigation systems, advanced propulsion, and new communication methods to deal with the object's unique path. The timeline for such a mission depends on how quickly 3I Atlas's orbit can be determined with certainty. If it stabilizes and remains in the solar system for many years, space agencies and private companies could develop a mission plan, build the spacecraft, and launch it within a reasonable period. This is a rare situation where the astronomical discovery aligns with technological readiness. The public interest in such a mission would likely be high. Interstellar objects capture the imagination because they come from somewhere else entirely. A mission to 3I Atlas would not only provide scientific data but also inspire curiosity and wonder on a global scale. It would be humanity's first close look at material that formed around another star, a direct encounter with something truly alien in origin. The potential success of a mission to 3I Atlas could also set a precedent for future quick-response missions to other interstellar visitors. Instead of being caught off guard as with Oumuamua, astronomers and engineers could have a standing mission framework ready to adapt to new discoveries. Over time, this could lead to a new branch of space exploration focused specifically on interstellar objects. The discovery of 3I Atlas came at a moment when astronomy is advancing rapidly. Telescopes are becoming more powerful, surveys more systematic, and space exploration more ambitious. This convergence of opportunity makes 3I Atlas not just a fascinating object in itself, but a catalyst for new scientific and technological developments. If it stays in our solar system, it might become a gateway to exploring the wider galaxy in ways that were previously only imagined in science fiction. Another fascinating part of the 3I Atlas story involves its physical appearance and behavior, which continue to intrigue astronomers as more data is collected. When the object was first detected, it showed a striking green glow that made it stand out clearly in telescope images. This glow is not unique to 3I Atlas, but it is visually impressive and gives useful information about its composition. The green color usually comes from diatomic carbon molecules. When these molecules are exposed to sunlight in the vacuum of space, they emit a green light, especially in the visible spectrum. This is often seen in some comets, and it suggests that 3I Atlas has volatile compounds on its surface that are reacting with solar radiation. As 3I Atlas moves closer to the Sun, the increased warmth causes these volatile materials to sublimate, meaning they turn directly from solid to gas. This creates a glowing coma around the object and sometimes a tail, depending on the activity. Observations so far suggest that 3I Atlas behaves partly like a comet, releasing gas and dust, but its activity level has shown some irregularities. These irregular patterns make it harder to predict its exact brightness and trajectory over time, but they also make it more scientifically interesting. Each burst of activity gives clues about what is happening beneath its surface. Studying the outgassing of 3I Atlas helps scientists understand not only the object itself but also the environment it came from. If it formed in a distant star system, the mix of ices and dust inside it might be different from those in solar system comets. By examining the gases it releases, astronomers can look for unusual chemical signatures. For example, differences in the ratios of carbon monoxide, carbon dioxide, or water vapor could hint at different formation temperatures or locations within its original star system. Another key aspect is the object's shape and rotation. With better telescopes and more observations over time, astronomers can track how the light reflected by 3I Atlas changes as it rotates. These brightness variations reveal information about its shape. Early indications suggest that it may not be a simple sphere. Like Oumuamua, it could have an elongated or irregular shape, which would affect how sunlight heats it and how gases escape from its surface. This, in turn, influences its movement in subtle but important ways. Understanding the rotation of 3I Atlas is also crucial for predicting its future path. If it rotates quickly and unevenly, outgassing can create small thrusts that change its trajectory over time. These non-gravitational forces are difficult to model, but they can make a big difference when predicting where the object will be years from now. Continuous observation helps refine these models and makes it easier to anticipate future behavior. The surface of 3I Atlas may also hold surprises. If a space mission eventually visits it, scientists might find a crusty exterior with layers built up over time as it traveled through interstellar space. Cosmic rays and micrometeoroid impacts could have altered its surface chemistry in unique ways. The outer layers may be quite different from the interior, which could still contain pristine materials from its formation billions of years ago. This makes it a kind of natural archive, preserving conditions from a completely different star system. There is also interest in understanding how long 3I Atlas has been traveling between stars. Interstellar space is vast, and objects like this can spend millions or even billions of years drifting silently before encountering another star system. By studying the weathering of its surface and the ratios of isotopes in its material, scientists might be able to estimate how long it has been exposed to cosmic rays and how far it has traveled. This would provide rare insights into the life cycles of interstellar debris and the movement of material between star systems. The glow of 3I Atlas has another useful side effect. Because it is visually distinctive, it is easier for astronomers and even skilled amateurs to track it against the background of stars. This continuous monitoring is essential for building an accurate orbital record. Every small change in position helps refine the models that predict its future path. The more data collected, the clearer the picture becomes of whether it will remain in the solar system or eventually escape. Interestingly, the public has also responded to the visual beauty of 3I Atlas. Astrophotographers have shared stunning images showing the glowing green object against starry skies, sometimes with long exposure shots that highlight its faint tail. These images not only support scientific work but also bring the story of 3I Atlas to a wider audience. Many people who might not normally follow astronomy have become curious because of the object's unusual appearance. As time goes on, scientists expect to learn even more about its physical nature. Changes in brightness, shape modeling, chemical analysis of its emissions, and orbital tracking all contribute to a richer understanding. Each observation brings new details, and together they help build a comprehensive picture of this traveler from another star. Unlike previous interstellar objects, 3i Atlas offers the possibility of long-term study, turning what might have been a brief cosmic encounter into an extended period of exploration and discovery. The discovery and study of 3i Atlas are also changing how scientists think about the solar system's role within the broader galaxy. For a long time, many astronomers viewed the solar system as relatively isolated, with few meaningful exchanges of material between stars. But the arrival of multiple interstellar objects within just a few years is forcing a reconsideration of this view. Instead of being rare, these events may be quite common, and the solar system might be constantly encountering drifting material from other stars. This has big implications for our understanding of galactic dynamics. Stars are not stationary. They move around the center of the galaxy, each following its own path, and their orbits bring them closer to or farther from one another over time. When stars pass through regions of higher stellar density, or near other star systems, they can exchange material through gravitational interactions. Small objects like comets, asteroids, or fragments of larger bodies can be ejected from their original systems and set adrift into interstellar space. Over millions of years, some of these wanderers inevitably encounter new star systems, including ours. If interstellar objects are common, then our solar system may be constantly sweeping up a steady flow of material from the galactic environment. Some of this material passes through quickly, while some may get trapped temporarily or permanently. This exchange of matter connects star systems in subtle but meaningful ways. It means that planets and comets are not just shaped by local processes, but also by galactic interactions. 3i Atlas is a perfect example of this galactic exchange. It likely formed billions of years ago around a distant star. Through some gravitational interaction, it was ejected from that system and began a long, slow journey through interstellar space. Eventually, its path crossed that of the solar system. Depending on how its orbit evolves, it may stay for a long time or eventually continue its journey. Either way, its presence here shows that the solar system is not isolated. It is part of a vast, interconnected galactic network where matter moves from star to star over immense periods of time. This idea has important consequences for theories about how life and complex chemistry spread through the galaxy. One hypothesis, called panspermia, suggests that life or the building blocks of life could travel between star systems on natural objects like comets or asteroids. If these objects can survive long journeys and remain relatively intact, they could potentially carry organic molecules or even hardy microbial life across interstellar distances. While there is no direct evidence yet that this has happened, the discovery of objects like 3i Atlas makes the idea more plausible because it shows that material really does move between star systems. Even if life itself does not travel this way, complex organic molecules certainly can. Observations of comets and interstellar clouds have already found a wide range of organic compounds. If 3i Atlas contains unusual organics that formed in a different star system, studying them could reveal how widespread the chemical precursors of life are in the galaxy. It could also show whether the same kinds of chemistry happen everywhere or if different environments produce very different results. The movement of interstellar objects also provides insight into the early history of star systems. When planetary systems form, many small bodies are left over. Gravitational interactions among forming planets can fling some of these out into space. Over billions of years, these ejected objects filled the galaxy, creating a population of travelers. By studying the properties of 3i Atlas and similar objects, scientists can learn about the processes that shaped other star systems long ago. Another fascinating angle is how these traveling objects interact with the solar system's outer regions. The outer solar system contains the Oort cloud, a vast and distant reservoir of icy bodies. Some researchers think that interstellar objects could occasionally collide with Oort cloud objects, or even become incorporated into it. Likewise, some Oort cloud objects might be ejected into interstellar space, becoming wanderers themselves. This constant exchange may mean that our Oort cloud contains not only objects formed here but also some that originated around other stars. 3i Atlas may be offering a rare chance to study such processes in real time. Instead of reconstructing ancient events through indirect evidence, astronomers can watch a galactic traveler interacting with the solar system as it happens. This helps refine models of how common such interactions are and what effects they might have on the long-term evolution of planetary systems. The idea that our solar system is part of a dynamic galactic environment adds a sense of wonder and scale to the story. It shows that the solar system is not a static place but part of a grand cosmic dance. Objects like 3i Atlas remind us that the boundaries between star systems are not solid walls but open pathways through which material flows slowly but steadily. Each visitor carries a piece of another star's history, and by studying them, we begin to see the galaxy as a living, interconnected system rather than a collection of isolated worlds. The presence of 3i Atlas has also sparked many new studies about how star systems capture and retain interstellar objects over long periods. Traditionally, astronomers assumed that most interstellar objects simply pass through quickly, following hyperbolic paths and disappearing into space after a brief visit. But if 3i Atlas ends up staying in the solar system for a long time, it could be one of the first clear examples of a successful capture in modern observations. This possibility is encouraging researchers to re-examine older data, run new simulations, and consider whether other captured interstellar objects might already be orbiting unnoticed in the outer solar system. Gravitational capture is a delicate process. It requires the incoming object to lose just enough energy during its interaction with the Sun and planets, so that its trajectory changes from an open hyperbola to a closed ellipse. Usually, this happens if the object has a relatively low approach speed and passes near a massive planet, most often Jupiter. Jupiter's immense gravity acts like a giant lever, capable of altering the course of passing bodies. Depending on the angle and timing of the encounter, the planet can either fling the object out even faster or slow it down enough for the Sun to hold onto it. If 3i Atlas is indeed captured, it would give scientists a rare opportunity to study the aftermath of such an event in real time. They could observe how its orbit stabilizes, how it interacts with the rest of the solar system, and whether its path eventually evolves into something more stable or chaotic. This information would help refine models of how the solar system accumulates and loses small bodies over time. Researchers are also looking into the possibility that some known objects in unusual orbits might already be captured interstellar bodies. There are several asteroids and comets with orbits that are difficult to explain through standard solar system formation scenarios. Some of these objects move in highly inclined or retrograde orbits, meaning they travel in the opposite direction to most planets and asteroids. Others have very long orbits that take them far beyond Pluto before returning. In recent years, scientists have begun to suspect that a fraction of these unusual objects might not have formed here at all. Instead, they could be relics from other star systems that were captured long ago. 3i Atlas can serve as a reference point for identifying such objects. By studying its motion, composition, and behavior, astronomers can create a profile of what a captured interstellar object might look like. They can then compare this profile to other bodies in the solar system to see if any share similar characteristics. This could lead to the discovery of a hidden population of ancient galactic visitors that have been quietly orbiting the Sun for millions or even billions of years without being recognized as such. Another intriguing question is how stable these captured objects remain over long periods. Some may stay for millions of years before eventually being ejected again through gravitational interactions. Others might settle into distant stable orbits and become permanent members of the solar system. If 3i Atlas enters a stable orbit, Tracking its evolution over decades will provide valuable insight into which outcomes are most likely. The study of captured interstellar objects also connects to bigger questions about the structure of the solar system's outer regions. Beyond Neptune lies a vast, sparsely populated area that includes the Kuiper belt, the scattered disk, and the hypothetical Oort cloud. These regions are not fully mapped, and many objects remain undiscovered. If interstellar bodies can be captured, some of them might be hiding out there in the darkness, faint and far from the sun. Detecting and studying these objects would require next-generation telescopes and long-term surveys, but 3i Atlas shows that such discoveries are possible. Captures may have been especially common during the early history of the solar system, when the sun was still surrounded by its birth cluster. At that time, nearby stars were much closer together than they are today, and gravitational encounters between systems were more frequent. This would have made it easier for material to be exchanged between young planetary systems. Some researchers think that a significant number of objects in the distant solar system might actually be remnants from that early period of stellar neighborhood interactions. If true, then the solar system is not just made of material that formed here but also contains fragments of many other ancient stars. The potential capture of 3i Atlas gives scientists a living example of this process in action, something they can observe directly rather than infer from models. By studying it closely, they can learn how often such events happen today and how they might have shaped the solar system in the past. This deepens our understanding of how planetary systems grow, evolve, and exchange material over cosmic timescales. Ultimately, this perspective shows that star systems are not closed, isolated entities. They are part of a vast galactic ecosystem where matter flows slowly but constantly between different stellar environments. 3i Atlas is more than just a passing comet-like body. It is a messenger from another star system, a piece of galactic history caught in the act of interacting with our own. By studying it, astronomers are not just learning about a single object but uncovering the hidden connections that bind together the stars of the Milky Way. The scientific interest in 3i Atlas also extends to the question of how interstellar objects like it are formed in the first place. Every star system produces countless fragments during its early stages of formation. When a new star forms from a collapsing cloud of gas and dust, the leftover material around it begins to clump together into planets, moons, comets, and asteroids. During this chaotic time, gravitational interactions between growing planets can be extremely violent. Large planets often fling smaller objects outward with tremendous force, sending them far beyond their original orbits. Many of these fragments escape the gravitational pull of their home star entirely and are ejected into interstellar space. This ejection process happens in nearly every planetary system. It is a natural byproduct of how planets grow and settle into stable orbits. When giant planets like Jupiter or Saturn form, they can act like gravitational slingshots, clearing their surroundings by throwing out smaller objects. Over millions of years, these ejected objects spread throughout the galaxy, becoming interstellar travelers like 3i Atlas. Some may wander alone for billions of years, others may encounter star systems and pass through quickly, and a few may get captured. The composition of these ejected objects depends on where they formed in their original star system. Those formed closer to their star may be rocky or metallic, similar to asteroids. Those formed farther out may contain more ices and volatile compounds, like comets. 3i Atlas seems to have characteristics similar to an icy comet, with visible outgassing and a green glow produced by diatomic carbon molecules. This suggests it probably formed in the colder outer regions of its original system, where sunlight was weaker and ices could accumulate without evaporating. By studying objects like 3i Atlas, scientists can learn about conditions in other planetary systems without having to send spacecraft to distant stars. Each interstellar object carries a kind of chemical fingerprint that reflects the environment it came from. For example, the ratios of different isotopes in its ices and rocks can indicate the temperature and composition of the region where it formed. The types of organic molecules found on its surface can reveal what kinds of chemistry took place in its birth system. This turns interstellar objects into natural messengers, bringing information from places we cannot yet reach directly. One of the most intriguing possibilities is that some interstellar objects may be fragments from planets, or even failed planets. During the violent early years of star system formation, collisions between planetary embryos are common. Sometimes these impacts shatter entire bodies, sending pieces hurtling into space. If those fragments escape the star's gravity, they can become interstellar travelers. This means that some objects wandering through the galaxy might be broken pieces of ancient worlds. If 3I Atlas were such a fragment, studying it could offer clues about the structure of planets that formed around other stars. The existence of a large population of interstellar objects also tells us something about how common planetary systems are. If most stars did not form planets, there would be fewer objects ejected into space. The fact that we have already detected several interstellar objects in a short time suggests that planet formation is widespread throughout the galaxy. This fits with what we know from exoplanet surveys, which have found planets around nearly every type of star. Interstellar objects like 3I Atlas are physical evidence of this galactic abundance of planetary systems. Another fascinating idea is that some interstellar objects might act as seeds for planet formation in new systems. When a star forms and begins gathering material, a passing interstellar object could be captured and incorporated into the forming planetary disk. This object could then act as a nucleus around which gas and dust accumulate, eventually growing into a new planet or moon. In this way, material from one star system could directly contribute to building another. This kind of galactic recycling may play a role in how diverse planetary systems arise. 3I Atlas is not just a visitor but also a representative of a much larger population of objects that fill the galaxy. These travelers are silent witnesses to the history of countless star systems. They have drifted through interstellar space, carrying traces of their origins, and when they encounter a star like our Sun, they offer scientists a brief but valuable chance to study that history up close. Understanding their formation, composition, and behavior also helps refine our models of galaxy evolution. The constant ejection and movement of material between stars mean that planetary systems do not develop in isolation. They are influenced by, and contribute to, the larger galactic environment. Studying 3I Atlas deepens our understanding of this vast interconnected system. In the end, the formation and journey of interstellar objects like 3I Atlas tell a story of movement, change, and connection on a cosmic scale. They remind us that the galaxy is not static but alive with drifting messengers from distant worlds, each carrying its own piece of the larger puzzle. By observing and analyzing these travelers, we gain insights into the processes that shape not only other star systems but also our own. The possible long-term presence of 3I Atlas in our solar system raises fascinating scientific questions. Unlike the first two known interstellar visitors which passed through quickly and disappeared back into deep space, 3I Atlas seems to have entered an orbit that is unusually stable. Current models suggest that instead of continuing on a straight hyperbolic path, it may have been slowed enough by gravitational interactions to remain bound to the solar system for a long time. This is extremely rare. Most interstellar objects travel at such high speeds that they are unaffected by the Sun's gravity except for a brief deflection. For 3I Atlas, something different may have occurred. One possibility is that 3I Atlas experienced a gravitational interaction with one of the giant planets, such as Jupiter, which altered its trajectory. Jupiter's massive gravity often acts like a gatekeeper, capturing or ejecting objects that pass nearby. If Atlas approached at just the right angle and speed, Jupiter's gravity could have deflected it in such a way that it lost enough energy to become temporarily captured. This kind of capture is more likely for objects that arrive with lower incoming speeds, and calculations suggest that Atlas's velocity relative to the solar system was lower than typical for interstellar visitors. Once captured, the object could settle into a long looping orbit around the Sun. The exact shape of this orbit depends on many factors, including the initial approach trajectory, the gravitational influence of planets, and non-gravitational forces like outgassing. Early orbital calculations indicate that Atlas might follow an elongated orbit that takes it far beyond the outer planets before returning inward again. If these models are correct, Atlas could remain in the solar system for centuries, or even longer before eventually escaping. A second possibility is that Atlas was not fully captured but has entered a weakly bound state, sometimes called a temporary gravitational trap. In this scenario, it is not in a stable orbit forever, but it is moving slowly enough relative to the Sun that it will take a very long time to leave. These kinds of orbits are chaotic and sensitive to small changes, so the object could remain for decades, centuries, or even millennia depending on future gravitational encounters. The idea that an interstellar object could stay in our solar system for such a long period is scientifically exciting because it provides a rare opportunity for extended observation. Normally, interstellar objects move so fast that astronomers have only a few weeks or months to collect data before the object fades from view. With Atlas, there may be many years to study its behavior, composition, and orbit in detail. This extended timeline opens the possibility of planning space missions to visit the object directly. If a spacecraft could be launched toward Atlas during one of its closer approaches, scientists could study it up close in a way that has never been done before with an interstellar visitor. They could analyze its surface materials, measure its exact composition, and possibly return samples to Earth. This would allow researchers to examine material from another star system in laboratory conditions, providing direct insights into the chemistry and formation history of distant planetary systems. Extended observation also allows astronomers to see how the object changes over time. Interstellar comets like Atlas may behave differently from comets that formed in our solar system. Their ices might contain different ratios of volatile substances, leading to unusual outgassing patterns as they approach the Sun. By watching Atlas through multiple orbits, scientists can learn how its activity evolves, whether its surface changes, and how its orbit is affected by these processes. Long-term capture also raises interesting theoretical questions about the dynamics of the solar system. If 3I Atlas can be captured and held, then it is likely that other interstellar objects have been captured in the past as well. Some may even remain undiscovered in distant orbits today, quietly circling the Sun as part of the solar system's population. Identifying such objects would deepen our understanding of how the solar system interacts with the wider galaxy. The fact that this capture may have happened naturally also helps astronomers refine their models of gravitational interactions. Studying the orbital evolution of Atlas can reveal how often these events occur and under what conditions. This improves predictions about the number of interstellar objects currently passing through or temporarily residing in the solar system. Finally, the potential long-term presence of Atlas connects to broader questions about the exchange of material between star systems. If the solar system can capture interstellar objects, then perhaps it can also capture material that carries organic molecules or even prebiotic chemicals. Over long timescales, such exchanges might play a role in spreading the building blocks of life across the galaxy. 3I Atlas may be the first clearly observed example of a captured interstellar object, but it likely will not be the last. Future surveys and telescopes are expected to find many more. The study of Atlas is therefore not only about one object but also about opening a new chapter in understanding how star systems share material across interstellar space. The idea that 3I Atlas may remain in our solar system for a long period has encouraged many astronomers to rethink how we search for and study objects that come from beyond our star system. For most of history, humanity did not even know that interstellar objects were passing through. They moved too quickly and were too faint to detect with older instruments. Only in recent years, thanks to improved telescopes, sensitive wide-field surveys, and advanced data processing methods, has it become possible to spot them. The discovery of 3I Atlas is part of this new era of astronomical observation, and it shows how much more we are capable of seeing compared to just a decade or two ago. The discovery also highlights how important timing and coordination are in astronomy. Interstellar objects can appear suddenly and move across the sky rapidly. Detecting them requires continuous monitoring of large portions of the sky. Once a candidate object is spotted, astronomers must act quickly to calculate its orbit and determine whether it truly comes from outside the solar system. In the case of 3I Atlas, this happened remarkably fast. Within a short time, astronomers confirmed that its trajectory was not typical of local comets. Its incoming speed and direction showed that it originated beyond our solar system, and its path indicated that it would not simply pass through and leave immediately like the earlier visitors. This rapid detection allowed researchers around the world to mobilize telescopes and gather a wide range of data before the object faded or moved too far away. Observations were collected in visible light, infrared, and radio wavelengths to build a complete picture of the object's properties. The green glow of Atlas, caused by diatomic carbon, made it particularly easy to track visually, even with modest telescopes. Amateur astronomers also contributed valuable observations that helped refine the object's orbit and monitor its changes over time. The case of Atlas has also encouraged scientists to develop better strategies for future discoveries. Space-based observatories and next-generation telescopes such as the Vera C. Rubin Observatory are expected to detect many more interstellar objects in the coming years. These facilities will scan the sky repeatedly and with high sensitivity, allowing them to pick up faint objects long before they get close to the Sun. With earlier detection, astronomers will have more time to plan detailed studies or even space missions to intercept these objects. Another important development is the improvement of orbital prediction software. Modern algorithms can process new observations in real time and quickly calculate whether an object has a hyperbolic or bound trajectory. In the past, this process could take weeks, during which valuable observing time was lost. Now, astronomers can determine an object's likely origin and path within days, enabling a rapid response. Atlas has also sparked discussions about international cooperation in studying interstellar visitors. Because these objects can appear anywhere in the sky and move rapidly, no single observatory or nation can monitor them effectively alone. Global networks of professional and amateur astronomers are essential for continuous tracking. Atlas demonstrated how coordinated observations from multiple locations can produce a detailed understanding of an object's behavior in a short time. The increased awareness of interstellar objects has changed how scientists think about the solar system's boundaries. It was once common to imagine the solar system as a relatively isolated place with a clear edge defined by the distant or cloud. Now it is clear that interstellar space and the solar system are constantly interacting. Objects come and go, sometimes passing through quickly, sometimes staying for centuries. This exchange is not rare or exceptional but part of the natural dynamics of the galaxy. By continuing to refine our detection methods and observational strategies, we will be able to build a catalog of interstellar objects, studying their properties systematically rather than relying on chance discoveries. Atlas is an early example of this future. The lessons learned from observing it are shaping how astronomers will handle the many new objects expected to be found in the next decade. The arrival of Atlas at this particular time is fortunate because our technological capabilities have finally reached a point where detailed study is possible. A few decades earlier, it might have passed by unnoticed. Today, however, we are equipped not only to detect it but also to follow its movements carefully, analyze its composition, and model its orbit with great precision. This combination of advanced technology, global cooperation, and scientific curiosity is what makes the study of Atlas so rich and promising. The story of 3I Atlas has also brought renewed public interest in interstellar exploration and cosmic mysteries. People around the world are fascinated by the idea that something from another star system has entered our cosmic neighborhood and may remain here for years or even centuries. It is a reminder that space is not empty but filled with travelers carrying the history of distant places. This sense of wonder has inspired many to learn more about astronomy, planetary science, and the nature of our galaxy. Avi Loeb, the well-known astrophysicist who has written extensively about interstellar objects, has played a key role in bringing attention to Atlas. Loeb has long argued that interstellar objects deserve serious scientific study because they may hold clues about other planetary systems, and in some cases, they might even show signs of artificial origin. His interest began with the earlier visitor, Oumuamua, whose unusual shape and motion sparked debate about whether it could be a piece of alien technology. While Atlas does not show the same unusual characteristics as Oumuamua, its long-term presence makes it an ideal candidate for extended research. Loeb has suggested that instead of waiting passively for these objects to pass by, humanity should consider actively exploring them. A captured or long-staying interstellar object like Atlas offers a rare opportunity for a spacecraft mission that does not require chasing an object moving at extreme speeds. If Atlas remains bound to the solar system, it could be visited using existing propulsion technologies. Loeb argues that such a mission would be scientifically invaluable, potentially revealing the chemistry, structure, and origin of a visitor from another star system. This idea fits into a broader vision of interstellar exploration. By studying objects like Atlas, scientists can gather information about other planetary systems without having to send spacecraft across vast interstellar distances. Each object acts like a messenger, carrying data about its home system and its composition and structure. A successful mission to Atlas could be the first step toward a new field of research focused on these natural interstellar messengers. The possibility of a mission to Atlas has already led to early discussions among scientists and space agencies. The main challenge is timing. Space missions take years to plan, build, and launch. If Atlas is indeed captured or bound for a long time, there may be enough time to prepare a probe to intercept it. The mission could be relatively low cost compared to missions to the outer planets because Atlas may make periodic close approaches to the inner solar system, depending on its orbit. A probe sent to Atlas could carry instruments to analyze its surface, measure its chemical composition, and take high-resolution images. It could deploy impactors or drills to study the material beneath the surface and detect trapped gases or complex molecules. These measurements would allow scientists to reconstruct the history of the object and compare it to comets and asteroids formed in our own solar system. Such data would help determine whether Atlas has typical cometary features or if it shows chemical signatures that are different, pointing to a foreign origin. Beyond the scientific benefits, a mission to Atlas could capture the public imagination in the same way that early space missions did. Sending a spacecraft to an interstellar visitor would be a historic achievement, demonstrating humanity's ability to reach out and study objects from beyond our star system. It would also symbolize the beginning of a new era in which the boundaries between star systems become more porous, not through human travel between stars, but through the study of objects that naturally move between them. Loeb has often emphasized that science advances most rapidly when bold ideas are pursued with determination. The presence of Atlas in our solar system is, in his view, a chance to take such a bold step. Rather than treating these objects as curiosities, they could become central targets for understanding our place in the galaxy. By exploring Atlas, we might not only learn about distant planetary systems but also refine our understanding of how the solar system itself interacts with the broader galactic environment. This perspective transforms Atlas from a passive object drifting through space into an active catalyst for scientific and technological progress. Its arrival at this time, when humanity has both the tools and the curiosity to investigate it, is more than a coincidence. It reflects a growing ability to notice and respond to cosmic events that would have gone unseen in the past. The next steps will depend on whether scientific institutions and space agencies choose to act on this opportunity. The scientific study of 3I Atlas is also helping refine our understanding of how objects from interstellar space behave when they interact with the solar system environment. As Atlas approaches the Sun, its surface warms, and ices buried beneath its outer layers begin to sublimate. This process releases gas and dust into space, forming a faint coma and sometimes a tail, much like a comet. By watching these changes carefully, astronomers can learn a great deal about the composition of the object and how interstellar material reacts to solar heating. One of the first things noticed about Atlas was its bright green glow. This glow is caused by diatomic carbon molecules. When these molecules are exposed to sunlight, they emit a distinct green light, which is often seen in comets from our own solar system as well. However, the intensity of the green glow from Atlas gives astronomers clues about the abundance of carbon-containing compounds in its ices. By measuring how this glow changes over time, they can estimate how quickly the object is losing material and what kinds of molecules are being released. Spectroscopic observations are especially valuable in this context. By splitting the light from Atlas into its component wavelengths, scientists can identify the chemical fingerprints of different molecules. This allows them to determine whether Atlas has a composition similar to comets from the solar system or whether it contains unusual chemicals that might indicate it formed in a different kind of environment. Early studies suggest that Atlas has a mix of typical cometary ices such as water, carbon dioxide, and carbon monoxide, along with traces of more complex organic compounds. These observations also help refine models of how interstellar objects survive their long journeys through space. An object like Atlas may spend millions of years traveling between stars, exposed to cosmic rays and extreme cold. Over time, its surface can become chemically altered, forming a kind of crust that protects the interior from further change. When the object enters a new star system and begins to warm up, this crust may crack, allowing fresh material to escape. Studying this process gives scientists insight into how interstellar travel affects the chemistry and structure of small bodies. Another important aspect is the way outgassing affects the object's motion. When gas jets out from the surface, it creates small but measurable forces that can alter the orbit over time. This effect, known as non-gravitational acceleration, was observed clearly in the case of Oumuamua and played a role in shaping its unusual trajectory. For Atlas, astronomers are watching closely to see whether its orbit changes in similar ways. Tracking these subtle shifts helps improve predictions of its future path and reveals how active the object is. The interaction between Atlas and the solar wind is also of interest. The solar wind is a stream of charged particles flowing outward from the Sun. When it encounters a cloud of gas and dust around a comet, it can create a shockwave and shape the tail of the object. By observing how Atlas's coma and tail respond to changes in solar activity, scientists can learn about both the object itself and the behavior of the solar wind. This makes Atlas not just a subject of study but also a kind of probe that reveals conditions in interplanetary space. Long-term monitoring is essential because Atlas's activity is not constant. It may flare up unexpectedly if new vents open on its surface, or it may quiet down as its ices are depleted. By keeping track of these changes over months and years, astronomers can build a detailed picture of how the object evolves. This information can then be compared with models of cometary activity to see whether interstellar objects behave differently. In addition to professional observatories, many amateur astronomers have joined in observing Atlas. Its distinctive green color and relatively bright coma make it a good target for medium-sized telescopes. Amateur contributions are valuable because they provide frequent observations from around the world, filling in gaps between major telescope sessions. This collaborative effort reflects the growing role of citizen science in modern astronomy, where enthusiasts can make real contributions to cutting-edge research. Through this combination of professional and amateur observations, scientists are gradually building a comprehensive understanding of Atlas's physical and chemical nature. Each new data set adds another piece to the puzzle, helping reveal the story of how this object formed, how it traveled across interstellar space, and how it is now interacting with our solar system. The study of Atlas is therefore not just about tracking its orbit but also about uncovering the deep chemical history it carries within it. The presence of 3I Atlas in our solar system also provides a unique opportunity to study how interstellar objects may influence their surroundings over long periods of time. If Atlas remains in orbit for centuries, its repeated passages through different regions of the solar system could create subtle but measurable effects. These effects might include depositing dust and gas in the outer regions, interacting gravitationally with other small bodies, and possibly even contributing material to the solar system's reservoirs of comets and asteroids. As Atlas travels through space, the dust and gas it releases form a diffuse trail along its orbit. Over time, this material spreads out and mixes with the existing interplanetary medium. In the case of regular comets, such dust trails can lead to meteor showers when Earth crosses their paths. If Atlas remains bound to the solar system for a long time, it is possible that its trail could eventually intersect Earth's orbit, potentially creating faint but detectable meteor activity in the distant future. Such an event would be an extraordinary reminder of the object's interstellar origin, as tiny fragments from another star system would burn up in our atmosphere. Gravitational interactions are another area of interest. Although Atlas is not massive compared to planets, its presence in the outer solar system could still have small cumulative effects over long timescales. If its orbit passes near other comets, asteroids, or trans-Neptunian objects, it could slightly alter their trajectories. These changes might be extremely subtle, but they could provide clues about Atlas's mass and structure. Tracking such interactions would require precise observations over many decades, but modern astronomy has the capability to monitor small orbital changes with increasing accuracy. Atlas could also act as a kind of tracer for studying the dynamics of the outer solar system. Its orbit may take it through regions that are otherwise difficult to probe, and by following its motion carefully, astronomers can learn about the distribution of mass and gravitational influences in those distant areas. This could improve our understanding of the structure of the Oort cloud and other poorly understood regions beyond Neptune. The chemical material released by Atlas as it warms near the Sun could also slowly mix into the solar system's environment. Interstellar objects often contain ices and organic molecules that formed under different conditions from those in our solar system. When these substances are released, they may provide rare samples of interstellar chemistry, enriching the local interplanetary medium with exotic compounds. Over long periods, such contributions might influence the chemical evolution of dust and gas in the solar system. Some scientists have even speculated that repeated encounters with interstellar objects over billions of years could play a role in the distribution of organic compounds, and possibly even prebiotic molecules, between star systems. This idea, sometimes called panspermia, suggests that life's ingredients may be exchanged naturally across the galaxy through drifting comets and asteroids. If Atlas contains complex organic molecules, as many comets do, then its long-term presence could contribute small amounts of these compounds to the solar system's reservoirs. Although the quantities are likely tiny, the cumulative effect over cosmic timescales could be meaningful. The long-term behavior of Atlas also offers insight into the stability and evolution of captured interstellar objects. If Atlas remains in the solar system for centuries, astronomers will be able to observe how its orbit changes due to gravitational perturbations, outgassing forces, and interactions with planets. This will help build more accurate models of how often such captures occur, how long they last, and what eventually causes the objects to leave. Some may remain indefinitely, becoming permanent residents, while others may eventually escape after one or more close planetary encounters. In addition to scientific research, the presence of Atlas could inspire future generations of astronomers and engineers to think creatively about how to explore interstellar visitors. While current technology might allow for a probe to visit Atlas, future missions could be more ambitious, involving sample return or even deploying multiple spacecraft to study different parts of the object simultaneously. Such missions could pave the way for a systematic exploration program focused on interstellar objects as a whole. Over time, Atlas may become a familiar name, much like famous comets that return periodically and are observed by successive generations. Its orbit could make it a recurring feature of astronomical observation campaigns, a steady reminder that the solar system is not isolated but part of a dynamic galactic environment. Its presence may also motivate further improvements in survey telescopes, detection algorithms, and space mission design, driving technological progress as scientists seek to learn as much as possible from this rare opportunity. In this way, Atlas is more than just a scientific curiosity. It represents a bridge between our solar system and the wider galaxy. Its extended stay gives humanity a chance to study interstellar material up close, to understand the processes that shape both local and galactic environments, and to imagine new ways of exploring space that take advantage of the natural movement of objects between stars. The extended study of 3I Atlas is also shaping new approaches to planetary defense and space monitoring. Traditionally, planetary defense programs focus on near-Earth asteroids and comets that pose potential impact risks. These objects usually originate within the solar system and follow orbits that can be predicted over long periods. Interstellar objects, however, present different challenges. They can appear suddenly, approach from unexpected directions, and move at high speeds. Atlas, with its slower trajectory and possible long-term orbit, gives scientists a valuable example to test how well current detection and tracking systems perform when faced with something unfamiliar. If Atlas had been on a collision course with a planet, early detection would have been crucial for any potential response. Observing how Atlas was discovered and tracked provides useful data for improving future systems. It shows where surveys succeeded, where delays occurred, and how communication between observatories can be optimized. This is important because interstellar objects, while rare, could in principle pose impact threats just like regular asteroids. Understanding their behavior and how to detect them early is a key part of preparing for such possibilities. Atlas also helps refine impact risk assessment models. Its trajectory, physical properties, and outgassing behavior differ from typical solar system comets, and this affects how scientists would model any hypothetical impact scenario. Studying these differences makes the models more realistic and flexible, capable of handling a wider range of possible objects. Even though Atlas itself is not a threat, it acts as a real-world test case for evaluating how planetary defense strategies might adapt to unexpected visitors. Another benefit is the improvement of long-term orbital prediction tools. Predicting the motion of interstellar objects that become temporarily captured is complicated. Their orbits can be chaotic, influenced by small gravitational nudges and non-gravitational forces like gas jets. By carefully modeling Atlas's orbit over time, scientists are improving their ability to forecast the paths of similar objects. This capability could be critical if a future interstellar visitor had a trajectory that brought it near Earth. The study of Atlas also highlights the importance of rapid decision-making when dealing with unusual objects. When something like Atlas is detected, astronomers must quickly decide how to allocate telescope time, which instruments to use, and whether any immediate actions such as spacecraft mission planning should begin. The experience gained from coordinating observations of Atlas will help streamline these processes for future discoveries. From a broader perspective, Atlas encourages scientists to think about planetary defense on a galactic scale. The solar system is not isolated, and over long timescales, it regularly encounters material from other star systems. Most of these encounters are harmless, but some could involve larger or faster moving objects. Understanding how often such encounters occur, and what kinds of objects are involved, is essential for building a complete picture of long-term impact risks. Atlas's orbit is particularly useful because it may remain stable for centuries. This gives plenty of time for astronomers to refine their tracking techniques and for engineers to think about what kinds of missions or defenses could be deployed if needed. In this sense, Atlas acts almost like a practice target for future scenarios. It is not dangerous, but it provides a realistic object around which planetary defense strategies can be tested and improved. Additionally, Atlas contributes to the broader conversation about space situational awareness. As human activity in space increases, knowing the positions and trajectories of natural objects becomes more important. Interstellar objects add another layer of complexity to this environment. Learning how to monitor and understand them helps ensure that future spacecraft, satellites, and missions can operate safely even as new and unpredictable objects pass through the solar system. The experience of tracking Atlas has already influenced how some survey programs operate. There is growing interest in expanding sky coverage, increasing the frequency of scans, and using artificial intelligence to identify unusual trajectories more quickly. These improvements will make it easier to detect future interstellar visitors early, whether they are harmless drifters or potential hazards. In this way, Atlas is not only a subject of scientific curiosity but also a catalyst for improving our ability to observe and respond to activity in space. Its presence highlights the fact that planetary defense must be adaptable and forward-looking, capable of dealing not just with familiar solar system objects but also with unexpected visitors from the wider galaxy. The presence of 3I Atlas has also opened new conversations in the scientific community about the broader role that interstellar objects play in galactic ecosystems. For a long time, the focus of astronomy has been on stars, planets, and the vast clouds of gas and dust that filled the spaces between them. Small objects like comets and asteroids were considered local features of individual star systems. The discovery of objects like Atlas has forced scientists to rethink this view. It is now clear that countless fragments are constantly moving between star systems, creating a subtle but continuous exchange of material across the galaxy. This exchange plays a role in shaping the composition of planetary systems. As interstellar objects drift through different regions, they can deposit dust, ice, and organic molecules, enriching local environments. Over long timescales, this mixing may contribute to the chemical diversity observed in planetary systems. It could explain why some elements and compounds appear in similar proportions in systems that formed under very different conditions. Interstellar visitors like Atlas act as carriers, slowly distributing material from their birthplaces to faraway regions. These objects may also influence the formation of new stars and planets. In dense molecular clouds where stars are born, drifting interstellar bodies can act as solid seeds around which gas and dust collect. This could accelerate the process of planet formation, providing ready-made cores that gather material more efficiently than dust grains alone. If Atlas had entered such a region in its past, it might have played a small part in the birth of new worlds before eventually being ejected again. The galactic distribution of interstellar objects also contains information about the history of star formation and planetary evolution. By studying their abundance, composition, and trajectories, scientists can infer how often planetary systems eject material and how far these objects typically travel. Atlas represents a single data point, but as more interstellar objects are discovered, a clearer statistical picture will emerge. This could reveal patterns in how different regions of the galaxy exchange material and how that influences their development over billions of years. Another fascinating possibility is that some interstellar objects may carry not only organic compounds but also complex molecules or even the precursors of life. The concept of panspermia proposes that life, or at least the ingredients needed for life, could spread from one star system to another through natural processes. If Atlas contains complex organics, As many comets do, then its presence in our solar system shows that such material can indeed travel between stars. Over time, countless similar objects could have seeded young planetary systems with essential building blocks, potentially influencing the emergence of life. This idea remains speculative, but the study of Atlas provides a real opportunity to test it. By analyzing its composition, either through telescopic observations or future space missions, scientists can determine whether it contains molecules relevant to prebiotic chemistry. If it does, this would support the notion that the galaxy is interconnected not just physically but chemically, with interstellar objects acting as messengers that carry vital ingredients from one place to another. The long-term presence of Atlas also means that its interaction with the solar system can be studied in detail over many years. This allows researchers to observe how interstellar material behaves in a new stellar environment. The solar wind, radiation, and gravitational influences gradually modify Atlas's surface and orbit, creating a kind of natural experiment that shows how foreign objects adapt to new conditions. Observing these changes provides insight into what might happen when objects from our solar system eventually drift into interstellar space and encounter other star systems. By examining Atlas's trajectory, scientists can also estimate where it might have come from. Its path through space before entering the solar system points roughly toward a region of the galaxy where it may have originated. While it is nearly impossible to trace its journey precisely due to the long timescales involved, statistical models can suggest likely source regions. This kind of research helps build a broader picture of how objects move through the galaxy, and how material from one region can end up in another. Atlas therefore represents more than a single interstellar visitor. It is part of a much larger and ongoing galactic process that links distant star systems through the slow but persistent movement of material. By studying it carefully, astronomers are not just learning about one object but also uncovering the hidden network of exchanges that connect the galaxy together. This new perspective transforms interstellar objects from rare curiosities into key pieces of the cosmic puzzle, helping explain how the galaxy evolves as a single, dynamic system over immense spans of time. The story of 3I Atlas also raises profound questions about how humanity might interact with interstellar objects in the future. For now, most observations rely on telescopes and ground-based instruments, but the idea of sending spacecraft to intercept and study these visitors is gaining momentum. If Atlas remains in the solar system for a long time, it could become a prime target for a dedicated mission. Unlike earlier interstellar objects that moved quickly and left before any mission could be planned, Atlas provides a rare opportunity because its trajectory is more stable and its speed is relatively low compared to hyperbolic passers. A mission to Atlas could give scientists their first close look at material from another star system. Spacecraft could map its surface in detail, study its composition directly, and even collect samples for return to Earth. Such a mission would be scientifically groundbreaking. It would allow researchers to compare Atlas's material to that of solar system comets and asteroids, revealing similarities and differences that would help trace its origins. Even tiny variations in isotopic ratios or molecular structures could tell us about the conditions in the region where Atlas formed. Planning such a mission would not be easy. Space agencies would need to design a spacecraft capable of rendezvousing with an object on an unusual trajectory. The mission would also need to be launched at the right time to minimize travel distance and fuel requirements. However, the growing interest in asteroid exploration and sample return technology means that the technical foundation for such a mission is slowly being built. In the coming decades, advances in propulsion and autonomous navigation could make interstellar object missions much more practical. Atlas could serve as a training ground for these future capabilities. Because it is not leaving quickly, engineers have more time to prepare and test mission concepts. This is very different from the brief windows of opportunity presented by objects like Oumuamua, which pass through the solar system too quickly for any spacecraft to catch up. By contrast, Atlas's long-term orbit gives humanity a realistic chance to plan carefully and execute a successful mission. Beyond pure science, visiting an interstellar object like Atlas would carry symbolic importance. It would be the first time humans reach out to touch something that came from another star. This could inspire a new generation of scientists, engineers, and explorers, much like the moon landings did in the past. The idea that fragments of other worlds drift through space and can be studied directly makes the galaxy feel less distant and more connected. It highlights humanity's growing ability to explore not just our solar system but the wider galactic environment. Such missions could also have practical benefits. Studying the structure and composition of interstellar objects up close might reveal resources that could one day be useful for space industry. Some may contain rare elements, unique isotopes, or even large quantities of water ice that could support future space operations. Although this remains far in the future, the presence of Atlas provides a tangible example that stimulates thinking about how humanity might one day interact economically or technologically with material from beyond the solar system. Another intriguing possibility is that interstellar objects could be used as stepping stones for deep space exploration. If objects like Atlas are found in stable orbits within the solar system, they could serve as waypoints or resource depots for spacecraft venturing further out. Their low gravity makes landing and takeoff easier than on planets or moons, and their alien origin makes them fascinating scientific targets. A network of such captured interstellar bodies could one day support missions traveling into the outer solar system, or even toward interstellar space. Atlas also brings attention to the need for international cooperation. Interstellar object missions would be complex and expensive, likely requiring collaboration between multiple space agencies. Coordinated observation campaigns, data sharing, and joint mission planning could maximize the scientific return and spread the costs. The global excitement generated by objects like Atlas provides a strong incentive for countries to work together, combining resources and expertise to achieve something that no single nation could do alone. Ultimately, Atlas represents a bridge between present-day astronomy and the future of interstellar exploration. Right now, it is an object that astronomers study from afar, using telescopes and calculations to understand its nature. But in the future, it could become a destination, a tangible piece of another star system that humans explore up close. This shift from passive observation to active exploration marks an important step in humanity's journey toward becoming a truly interstellar civilization. By studying Atlas now and preparing for potential missions, we are laying the groundwork for a new era of discovery that reaches far beyond the boundaries of our solar system.